Okie dokie. So we are in the middle of showing you how to do trigonometric substitution, right? Remember that trigonometric substitution is just a matter of remembering the Pythagorean identity, right? So as long as you remember the Pythagorean identity, you can do the trigonometric substitutions. Okay, so remember last time we had this example. So Pythagorean identities, cosine squared plus sine squared equals 1. 1 plus tangent squared equals secant squared, right? So in fact, you don't have to remember both of them. As long as you remember one, you can get the other by dividing, right? Okay, and you remember the idea was like this. We had this example of integrating 1 over 1 minus x squared, right? 1 over 1 minus x squared. And what we're hoping, so you think, okay, I've got this radical, right? I've got this root here. I want to get rid of that root by changing this thing to a square, right? So your thought is, I want to make 1 minus x squared into something squared, right? I want to change it into something squared, right? Because then I've got the square root of something squared, which is better, which is good, right? And maybe I've got some hope of getting rid of the radical then. Okay, so you think of that, right? Like, boy, I wish I could get rid of that radical. And then you think, okay, well, if I say, look, let x squared, let x be sine, right? So you go back to your Pythagorean identities and you say, well, look, if I have 1 minus sine squared, that's cosine squared, right? Cosine squared plus sine squared is 1. 1 minus sine squared is cosine squared, right? And so that's promising, right? So you say, okay, maybe I'm going to change this. I'm going to let x be sine of t, right? Because then I'll have 1 minus sine squared, which is cosine squared. I'll have the square root of cosine squared, right? So that's how you think, right? If you see something like this, you go back here and you say, well, okay, how am I going to get rid of this thing? How am I going to make this thing into a square? And then you go from there. If this were 1 plus x squared, what would I think? What would I use? 1 plus x squared. What am I going to think to make the x? Tan, right? Because then I have 1 plus tan squared. Well, that's secant squared. I have the square root of secant squared, right? Okay. So, now, just one thing to remember is that when you're doing this, right, this is like your u substitution. And the way we're writing it is sort of backwards from the way we wrote the u substitution, right? Because when you write the u substitution, it's usually like u is some function of x, right? U is some function of x, rather than writing x as some function of u, right? It doesn't matter too much, but really what we're doing here is we're letting t be sine inverse of x. Okay, just to make the link back to u substitution more clear, right? What you're really doing is you're saying, I'm going to make a new variable u or t, whatever you want to call it, and that guy is going to be sine inverse of x. Okay. Okay, but you can write it this way. It's fine. Doesn't matter. The main point here is that this gives you some constraint on what t can be, right? T lies between negative pi over 2 and pi over 2. Right. because it's sine inverse. Yes, Mr. Placid.
Can you use also x equals to cosine?
Yes, yes. So we said this last time, right? If we could just as well take 1 minus cosine squared, and then we replace with then would this be the square root of sine squared?
You still get the same answer.
You should get the same answer, or something that's equivalent to the same answer. It may not look the same, but it will be equal to. Yes.
And why do we know it has to be on the interval?
That's from the definition of sine inverse. That's from the definition of sine inverse. So remember, this is what we did over here last class, right? What is sine inverse? What is sine inverse, right? Well, sine inverse is the inverse of sine, right? Inverse of the sine function, right? But remember, the sine function is not invertible, right? The sine function is not invertible because, it's a many-to-one function, right? Okay, so it's the inverse of the sine function restricted to negative pi over 2, pi over 2. So you may remember when you did inverse functions in pre-calculus or calculus, Calc 1, you said, well, look, we can't invert the sine function, right? Because you have to pass, in order to be invertible, you have to pass a horizontal line test, right? This thing very much fails the horizontal line test. And so you say, okay, I'm going to restrict my function to negative pi over 2, pi over 2, and just ignore everything else, right? So this is, now we're looking at the sine function restricted to negative pi over 2, pi over 2. Okay, right? And this function is invertible, and we call the inverse sine inverse. Okay, so, but then if you're talking about sine inverse, the outputs are going to be in negative pi over 2 pi. Yeah.
And with the area of that cross out? With the area between negative pi over 2 and pi over 2 cross out?
What do you mean cross out?
Like, would it equal 0?
If you took the integral of that, yeah, that would be 0. Yeah. It's the same. Yes, Mr. Mystery.
Do you have an answer for the problem you posed up there, 1 over square root of 1 minus x squared dx?
Yeah, we did it last time. Remember, it was sine inverse. Yeah. So this is what we did. We finished up class with last time. It turned out to be sine inverse. Okay. So this is what we did at the end of class. This is the last thing we did, or the first thing we did in this section. Okay, so that was the example, right? And just to give you a sense of the method, right? And the method is, just try and figure out how to get a square in here using the Pythagorean identities, right? That's the strategy. Strategy: make this thing into something else. Whatever you got here, try to make it into something else squared, right? Yeah. Whatever you have, try to make it into the square root of a square. Okay. So here we can sort of write down a method. If you see the square root of x squared plus a squared, substitute x as a tangent beta. Right? Let x be a tangent theta, right? Because then you'll get a squared tangent squared plus a squared. Right? Is that clear? confused by that?
Like, elaborate on that.
Yeah. So if we let x be a tangent, we're going to get a squared tangent squared plus a squared. Right? This thing would change into this. That's great. Why is that good? Because that's a squared tangent squared plus 1. So that's a squared secant squared. Right? So then we get the square root of a square, which is what we're hoping for. Okay. Okay. So if you see something like this, you take this substitution with where beta lies between negative pi over 2 and pi over 2, right? Because we're using the arctan. If you see x squared, if you see a squared minus x squared, you let x be what? Take half a minute, take 30 seconds and write down what this should be. Don't blurt it out. Don't blurt it out.
Just a guess.
Okay, turn to somebody nearby and talk with them. Tell them what you read. Okay. Okay, so what do you choose? What did you write? What do you write? Somebody? Anyone?
We said it's either cosine or sine.
Yeah, so either a cosine or a sine. I'm going to stick with a sine. So where beta lies between, again, negative pi over 2 and pi over 2. Okay, and then the last one, if you see x squared minus a squared, then you take x to be, again, take half a minute and write something down. Okay, turn to somebody nearby, tell them what you wrote. Okay, somebody want to tell me? Kara, how do you say it?
Kara.
Kara, excuse me. A secant, yeah, a secant. And a secant theta, where now the thing for theta is a little bit tricky. So you say with theta in 0 pi over 2 for x over a greater than equal to 1, and theta in pi over 2 comma pi for x over a less than negative 1, less than equal to negative 1. Again, that's just based on how the arcsecant is defined. Okay. So you might think, oh, I have to remember all this, but the thing is that you don't, right? Just remember the Pythagorean identities, and then figure out from there what you need to do. Okay, so I never remember this. Don't memorize this. Understand the idea. Okay, so let me have you try one. Here it is. Dx over x squared plus 1 quantity squared. Okay. Now this one doesn't even have a radical in it, so you might think, well, why am I going to use trigonometric substitution? It's okay. Use trigonometric substitution and you'll see that this works. You can get this. Even if it doesn't have a radical, you can still use trigonometric substitution if you feel like it. And we feel like it. Okay. So take 2 minutes and see if you can get somewhere on this. Okay, talk to somebody nearby. Okay, so what are we going to take as our substitution? It's pretty clear, right? Tan, right? Right, because we have 1 plus tangent squared equals secant squared, right? So you say, oh, look, you know, if I do that, then I can change this thing into a square. Okay, it's okay. But dx is going to be what? Secant squared theta d theta, right? And so we change this thing into secant squared theta d theta over 1 plus the tangent squared plus 1 quantity squared, right? So you get secant squared over secant to the 4th d theta, right? Everybody okay? Right? Nothing amazing. So we get secant to the negative 2 d theta, right? Secant to the negative 2. Well, secant to the negative 2 is the same thing as cosine, right? 1 over the secant is the cosine. So let's switch this to cosine, right? Now we've got cosine squared, the integral of cosine squared. Well, this was one of the things we saw last time. There's a trigonometric identity to use here, right? So we use that double angle formula, and we get 1/2 1 plus cosine 2 theta. Okay, everybody okay up to this point? Anybody have questions? Yes, Kara.
I guess this why you had to put on top for the dx.
Well, dx is secant squared theta d theta, right? So I'm doing my substitution. So I'm not going to leave this as d. I'm not going to leave this thing as dx, right? I have to change this. I have to change. I'm changing my variable from x to theta, right? So x turns into x is tangent theta. dx d theta is secant squared theta.
Is that like the same as u sub?
Yes, exactly. Yeah. It's basically the same thing you do in u substitution.
Can you explain the last line again?
From here to here?
Yeah.
This is just a trigonometric identity that we mentioned last time. You remember we had these two formula. Sine squared is 1/2 1 minus cosine 2x. Cosine squared is 1/2 1 plus cosine 2x. Okay.
So if we didn't step, we wouldn't be full kind of.
We still haven't finished.
Oh.
We still haven't finished. Okay. It still goes on. Okay. Even if you get to here, you're not going to get to there. Okay. So, right, so we've got 1/2 the integral of 1 plus cosine theta. Right? What does that turn into? You get 1/2. The integral of 1 is just theta. Thank you. And the integral of cosine 2 theta is going to be, somebody just say it. Anybody? 1 over this 1/2 sine 2 theta plus constant. Right? You get 1/2 theta plus 1/4 of sine 2 theta plus constant. Okay. And you think you're done, but you're still not done, because we have to switch this back to the original variables. Okay, we have to switch this back to the original variable, x, right? So what's theta? Arctan. So you get 1/2 arctan x plus 1/4 of sine of 2 arctan x. Okay. Okay. So you get sine. Okay, so let me make this a little bit. So let me say it this way. Sine of 2 arctan x. Let's see. Okay. Right, theta is arctan. Yes.
Could you briefly go over how you got from inverse secant squared, like in arc secant squared to cosine squared?
That's not arcsecant. That is,
Or secant to the negative?
that's secant to the negative 2. So
yeah.
maybe I should not write it like that since it's so confusing.
Okay.
Yeah, that's secant to the negative 2. I'm sorry. Because I had secant squared over secant to the 4th. So I get secant to the negative 2.
And how did you get from that to cosine? Is that just the identity?
The secant is 1 over the cosine,
Okay.
right?
Yeah.
So 1 over the secant is the cosine,
Okay, that makes sense.
right? So we've got 1 over secant squared, so that's just cosine squared. Yeah, sorry about writing it like this the other way. That's confusing.
Would you have to write cosine also negative 2, or it just becomes
It's secant to the negative 2,
That's
right?
what we did.
Secant to the negative 2 is cosine squared, right? It's not cosine to the negative 2. Right. That would be, cosine to the negative 2 would be secant squared. Okay? Okay, we're still not done. Still not done. Okay, so in some sense we're done. Okay, so you could at this point sort of declare victory, right? We've gotten back to our original function, our original variable. But typically we want you to go a little bit farther than this. Okay, you can simplify this a little bit more. Okay, and let me show you how to do it. Say, okay, well. Okay, so the first thing is that the sine of twice an angle. Does anybody remember the double angle formula for the sine? So sine of twice the angle is 2 times the sine of the angle times the cosine of the angle. Okay. Everyone all right with that? That's just a trigonometric formula, right? Sine of 2 theta is 2 sine theta cosine theta. Okay. And then the second thing is that you can actually simplify this thing a little bit farther. So what's the sine of the arctan? What's the sine of the arctan? You think like this. Okay, if this is arctan x, then what's the tangent of that? The tangent of arctan x is just going to be x, right? Okay, so I know that the ratio of these sides is x to 1. Right? Opposite over adjacent. Right? The tangent of this is x. In other words, these sides have this ratio. Okay. That tells me that this side length is 1 plus x squared. Right? And so what's the sine of it? What's the sine of arctan x? Well, the sine is going to be x over this, right? It's x over this. Okay. What about the cosine? Well, the cosine is going to be the adjacent over the hypotenuse. Okay. So we can write this thing more simply as 1/2 tan inverse x plus 1/4 of, 1/4 times 2, so that's 1/2 of sine times the cosine plus c, right? In other words, you get 1/2 tan inverse x plus x over 2 times 1 plus x squared plus c. And now you are done. That's about as far as you can go in making it simple.
We should be expected to know this stuff by the midterm.
No, what stuff?
Like the 2 sine tan negative 1x cos negative 1. Like those properties.
Do you mean like the trig identities?
Yeah. Like,
Well, I don't think I'm going to ask you some trig identity. And the examples on the midterm, the problems on the midterm will be simpler than this. You see how long it took us to do this one problem, right? So yeah, it's pretty unlikely that I'll ask you some obscure trigonometric identity. But you should be able to do something like this. Right? If I say, what's the sine of arctan of x? Well, you can figure it out using a triangle. You say, well, look, I can figure if this angle is arctan, then the tangent is x. That means the ratio of opposite to adjacent is x to 1. That gives me that the length of the hypotenuse would then be the square root of 1 plus x squared, right, by the Pythagorean theorem. Right? And then from there you can figure out all angles, right? You can figure out the cosine, whatever. Okay. So this is useful. Right, so there's kind of two parts to this, right? The first is doing the substitution, and then the second is switching it back to reversing the substitution, getting back to your original variable. Let's see. Okay. Let's do another one. Okay, so yeah, let's do this one. Okay, so the integral of dy over y times the square root of 1 plus natural log of y squared. Okay. So first figure out what you're going to do for your substitution. Think for half a minute and then tell me what you would do for your substitution. Turn to somebody nearby and help with them, please. So what's the Pythagorean identity that we're going to use? 1 plus something squared equals something squared, right? What is it? 1 plus tangent squared equals secant squared, right? Right? 1 plus something squared equals something squared, right? Something else squared, right? So we want to make this thing tangent of whatever variable is tan theta. Okay, so let natural log of y be tan theta. Okay, so this is a little bit more sophisticated than the last example. We're not taking y to be equal to tangent, we're taking the natural log of y to be the tangent. That's still okay. Okay. You see that there's some versatility to this technique. Okay. Okay, now we differentiate both sides, right? And what do we get? 1 over y dy equals secant squared theta theta. Right? Okay, which is great because we've got this dy over y here. Right? Okay. Okay, so now we say, okay, now let's switch it over using our substitution, right? So we get dy over y. This dy over y changes into secant squared theta d theta, right? Our 1 plus natural log squared turns into 1 plus tangent squared. Right? And again, here, because we're using the arctan, theta lies between negative pi over 2 and pi over 2. But non-inclusive. Okay, so this turns into secant squared over the square root of secant squared, right? 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 And so we get this turns into the absolute value of the secant. Can we get rid of the absolute value signs? Yes, we can, right? Because theta lies between negative pi over root and pi over 2, so we're on the right side of the plane, right? And secant is 1 over the cosine, so which is positive on the right side of the plane. Okay, so we can say that this is just secant squared. Initially, we say that it's the absolute value of the secant, but then we can get rid of the absolute value signs. Because we have the range of theta. Yes?
What would be an example of when you can't get rid of the absolute value sign? Would you redefine theta as something?
You'd have to split it into 2 parts then, like so. Yeah, but almost invariably in these problems it works out. Yeah. Okay, so this turns into the integral of the secant, right? But this is one that we did last time, plus the integral of the secant. You remember, you have this funny trick of multiplying by 1 secant plus tangent over secant plus tangent, and you end up with the natural log of the absolute value of the secant plus the tangent. Okay. Now we play now we have to get back home to x, right? To y, excuse me. Yes, thank you. Part of it is easy. Tan theta, we define to be natural log of y at the beginning, right? So that's easy. Secant theta, well, that's going to be, so tan theta is the natural log of y. So theta is the arctan of natural log of y. Right? So again, we play our game. Right? If this is theta, then we know its tangent is the natural log of y. Right? The tangent the ratio of the opposite to the adjacent is the natural log of y. Right? And so, you know, the third side has to be like this, the square root of 1 plus natural log y squared. That right there. Right. Then the secant is 1 over the cosine. So it'll be the hypotenuse over the adjacent. Right? So you see that the secant of theta is going to be the hypotenuse over the adjacent, which is what? Right? And so what do we get? We get the natural log of the absolute value of square root of 1 plus natural log of y squared plus natural log of y plus c. Okay, so again, you see the game, right? Figure out your substitution using the Pythagorean identities, right? Do the integral with the new variable, and then switch back at the end. Switch back at the end to your original variable. Okay. First Elizabeth, yeah.
For the triangle, are you just assigning like arctangent to either one of those angles just to help you figure it out? It doesn't
Yeah,
matter?
yeah,
Okay.
yeah. I mean, you could put it here if you felt like it.
Yeah,
It makes no
okay.
difference. Debbie.
I'm confused why you brought back the absolute value.
Why I got the absolute value? That's from last time. We saw last time that the integral of the secant is the natural log of the absolute value of the absolute value. And maybe I'll explain it to you after class. Okay. I'll show you the derivation after class. Other questions? Yes?
In terms of ideas, the tangent of 1 over y is y.
Uh-huh.
Can you explain that?
So, what's the derivative of the natural log? So, right, so you get, you have some, right, it's clear. Okay. You get 1 over y dy. Yes, Sam?
When you're assigning the triangle,
Yeah.
how are you saying that inverse tan is equal to ln? Wouldn't it, if you're assigning the triangle, wouldn't it be instead of opposite over adjacent, would be adjacent over opposite since it's arctan right now?
No, this thing is so this thing is arctan natural log y, right? That means that its tangent, the tangent of this angle is natural log y. The tangent, this is this angle, it's this guy. The tangent of this angle is natural log y, right? Which means that the tangent, namely the ratio of this to that, must be natural log of y to 1. Okay, that's it for today.